Okay, so let's talk about the quiz for a minute. And just to give you a heads up, I did not grade this quiz. My grader graded it. So if you have a question on the points, let me know. And I can look at it again and see. On problem 1, setting the denominator equal to 0 was worth points. So if you did that, a lot of you said x equals 0, which was half right, except for the fact that some of you explained x equals 0 because the numerator can't equal 0. And I was just looking through a couple of them. That made me a little concerned. You only have a problem when the denominator equals 0. So by writing this equals 0 and then solving for 0, you got your two answers, x equals 0 or x equals minus 1/2. Those are the problems. So the function is continuous at all points except at x equals 0 and x equals minus 1/2. So depending on how they word the problem, if they ask for the interval in which it is continuous, you would say minus infinity to 0, minus infinity to minus 1/2, union, minus 1/2 to 0, union 0 to infinity. And so some of you did that, which was fine, but just to note that if they're just asking for the values of x, which the function is not continuous, you only have to really list those two values. Does anyone have any questions on that? Being worth 4 points, a lot of you just got 1 point for saying 0. Next question, pretty straightforward. We did a couple of examples in class of this. To find if it's continuous, find the value of k that makes this function continuous. The limit on the right has to equal the limit on the left has to equal the value of the function at the point. So you're solving the linear expression 24 equals 4k. And that k to satisfy that would be 6. Number 3. A lot of you knew the answer was going to be not 5, but 4. 20 over 5 is 4, not 5. So when I upload that, I should have that fixed. But other than that, the important part is to show this goes to 1 and this goes to 1. You can't just assume tangent of 20x over sine of 5x goes to 4. It is true it goes to 4, but why does it go to 4? So in calculus, I can teach, a 4-year-old all these little tricks. But if they don't understand why, they don't know calculus. They don't understand calculus. They can memorize tricks. When I see this equals 4. I don't know why it equals 4, but it equals 4. So the important part here is to show why this equals 4. The reason why it equals 4 is because we know this by the squeeze theorem goes to 1. We've shown that. The squeeze theorem was an intense theorem. We went through and said, okay, that smaller triangle, the sector, and the larger triangle, those all are related. The smaller triangle is always going to be smaller than the sector. That sector is always going to be smaller than the larger triangle. We went through and proved that the limit as x goes to 0 of sine of x over x is 1. So we can use that to be known because we understand the proof of it. We spent the time to go through the proof of it. Here, we didn't prove that tangent of 20x over sine of 5x is 20 over 5. It turns out it always is 20 over 5, but the reason why is the work shown there. Question?
I got it right, but I was wondering, whenever you drop the x's after the 20 and 5, is that because they cancel?
Yes, x over x goes away. Yeah, so I try to kind of show that here as them canceling, or this 20x canceling with this x, and simplifying it. So number 4. There's a couple different ways you could write it. You could write it as sine of x over x quantity squared, and we know that goes to 1. So we're left with 1/2 times 1, or 1/2 times 1 squared. We get a half there.
Excuse me, the answer is short, so do you consider like giving only the answer half points?
The answer's worth 3 points, and the work's worth 3 points. So this is, if I can kind of show you, this is what I give my grader. And I tell her this is worth 2 points. So there's some consistency there. So if you feel like, oh, she took off a lot of points, so she did that consistently, theoretically consistency for everyone. So I said, okay, knowing this or this is worth 3 points. Knowing that it goes to 1 is worth 3 points. And the answer is 3 points. So showing your work there is worth points. Here, these are just worth a point each. So if you have questions on how it's graded, specifically, you can turn it in and I can relook at it. So part of being a graduate assistant is grading. So then if you go to teach, then you kind of have an idea of how to grade things consistently. We're human. We mess up. So, I mean, don't be afraid to approach me with something. And I can explain why I think that may be, or I can reevaluate it at that point. So, anyone come in and needed their quiz? Okay, so we talked about 2.2, 2.1 and 2.2, and these tangent line and rates of change, and then the derivative function. I gave you that review sheet for the first exam. The first exam will only cover up to 2.1. So we're going to go over things this week. It's not going to be on the first exam. It will be on your second exam, and you will be responsible for that. So you have to kind of balance, okay, studying for the exam on Thursday, but keeping up with the material as the weeks go. So the quiz will be uploaded after class. We might pull up the theorems from the book. There's quite a few theorems in 2.3, but they're pretty short, so I end up writing them out.
Which homework?
Most of the time. Just 1.6 is due tonight. And 2.1 and 2.2 I just assigned, and they'll be due next Monday. But keep in mind, 2.1 will be on that first exam, but the Wiley homework won't be officially due until next Monday. But you might want to look it over and make sure you can do it. Question?
The quiz next week.
There's not a quiz next week. There's an exam on Thursday. This week. Sorry.
Next week, 2.2 through whatever.
Yeah.
Okay.
Yeah. What we'll cover basically this week.
Okay.
Question?
What time was the homework supposed to begin?
5 o'clock.
Okay, so I went upstairs and put it in the
Yeah, that's fine. I got it.
Okay.
Yeah. I'm about halfway through grading the homeworks, so I should have them tomorrow. So you could have them back and look them over before the exam. So, any other questions? Okay, so today we're going to cover 2.3, which is going to be, what is today? 2.3 is going to be techniques, or an introduction to techniques of differentiation. Which we're going to learn shortcuts. From now on out, we're going to learn shortcuts in how to differentiate functions. So before we learn the definition of the derivative, so if you recall 2.2, we defined the derivative of the function was to be the limit as h goes to 0 of f of x plus h minus f of x over h. So we spent time in doing examples from this. 2.3, we're going to learn a couple theorems that's going to simplify this. However, on this first exam, if I say by the definition of the derivative, you need to use this technique to differentiate it. But you can know the power rule to say, I know what the derivative is going to be, but I need to show it by this limit as h goes to 0 of the difference quotient. So let's find what would be the derivative of a constant. So let's take a function, f of x, and call it c, where c is a constant. And if I do it by the definition, I get the limit as h goes to 0 of c plus h minus c over h. And I'm getting some feedback again. Okay, so. Oh, sorry, not c plus h. There's no h there. Right? If I replace f of x plus h, that's just c. There's no variable to plug in x plus h, right? There's one step down. Does that make sense? There's no x. So if I replace, this function is 5, right? If I replace the variable in the function with anything else, I still just get 5, right? It's always the constant. So what this here is 0 over h. So we've talked about before, something going to 0 over something going to 0, we have to do work, right? We can't just conclude. But 0 over something going to 0 goes to 0. There's a difference in something going to 0 and something being 0. Does that make sense? Here I have something that's 0 over something going to 0. So I could test points around 0, right? The left side of 0. What's 0 over negative any number? It's 0, right? 0 over negative, or 0 over any positive number is going to be 0. So if I test points on the right and the left, I'm going to go to 0. So the 0 over something going to 0 is 0. But be careful, something going to 0 over something going to 0 is indeterminate, and you have to do some work there. So you see the difference? This is 0, it's not going to 0, or this is going to 0. Something 0 over something going to 0 is 0.
The limit of the constant's always 0.
Yes. So what I'm saying here, that the derivative of a constant, so I'm going to write this a little differently. So the derivative with respect to x of a constant function, any constant, the derivative of 5 is 0, which makes sense if you think of the graph. So let's name this constant c. What's the slope at any point? And that's what the derivative is, right? Slope at any point is 0. So it makes sense that the derivative of a constant is 0. And we can prove that by the definition of the derivative.
Can you explain that notation?
This notation here? Yeah, so in 2.2 we talked a little bit about, I don't know, did we get into some notation of Newton-Leibniz? Okay, so this is just saying I'm taking the derivative of whatever's in parentheses with respect to x. So I could have f prime of x. I could write that as this. So they're saying I have this function f of x and I'm taking the derivative. This is saying this function f of x, this is a differential operator on this function. Does that make sense?
Is that the same as dy over dx?
Yeah, so generally we could say something like y equals f of x. So I could say the derivative of y with respect to x equals, right? So kind of this is understood that it's the derivative with respect to x of my function y. I'm calling my function y f of x. So yeah, these are all equivalent notation for derivatives. Okay, so derivative of constant is always 0. Huh?
Will that be used like that notation on quizzes?
Possibly. It's used in your book. It's used on Wiley. They use a different notation throughout. The benefit here is saying I know my function's called y, and I'm differentiating with respect to x. Eventually, in Chapter 3, we're going to learn logarithmic differentiation and implicit differentiation. So I might be differentiating a function with respect to y, and I name that function x. So you might have, you know, in Chapter 3, you might have the derivative with respect to, you might have something like this. The derivative of the function name, your function would be a function of y. And so dx dy means I'm differentiating this function, but with respect to y. So this notation has its benefits versus just the prime notation. And we'll get to that in Chapter 3. So, question?
Can you explain what a derivative is?
The derivative, by definition, is this. What it means is the value of the slope at any point. That's a good question because you want to think about what we're doing here. So if I have a function, the derivative at a point, if I plug in the point, it's going to give me the slope at any point. So if I plug in this point here and I want to find the derivative, I find the derivative and I plug in x equals whatever this point is, it should give me what the slope is, the value of the slope here. So if I plug in this point, the derivative would be 0. If I plug this point into the derivative function. So if I have the function f of x, eventually I can have a function f prime of x, which would be something like this on top of this function here, that it's positive here, then it goes to 0, then it's negative, then it goes to 0, then it's positive again. So this would be f prime of x. So So these functions, yeah, so if I differentiate this function, this function represents the slope at any point. So if I plug in a point to the derivative, it will give me the slope at that point of the original function. We can find that by definition by doing this to find the equation. And then once I have the equation, I can plug in any point, and that will give me the slope at that point. And then I can find the equation of the tangent line using point and slope. But that's always a good thing to be asking yourself. What does this mean? So these are all different notations for the derivatives. If we want to look at derivatives of power functions, let's look at differentiating with respect to x of x. What's the derivative of x? We could use the limit, take the limit as h goes to 0 of x plus h minus x over h, which would be the limit as h goes to 0 of h over h, which would be the limit as h goes to 0 of 1, which would be 1. Turns out the derivative of the function x is 1. What's the derivative of x squared?
Can you go back to that real quick?
Yeah, sorry. What's the derivative of x squared? Do you guys remember doing x squared? 2x. And it turns out theorem 2.3.2 in your book states that the derivative with respect to x of x to the nth power is n x to the n minus 1. 2.3.3 extends n to be any real number. So generally we think of n being an integer, right? We think like the derivative of x to the 5th, 5x to the 4th. But you can also do it with fractions, negative numbers, things like that, as long as n is any real number. So there's two theorems here. They both state the same thing. The first theorem proves it for n being an integer by using binomial theorem. Because if you think about the x to the 8th power, if you were to prove that, you'd have to have x plus h to the 8th power. So you're going to have to use binomial theorem and have this really large polynomial. But eventually, you take the limit as h goes to 0, and all the other terms with h's in it goes away. So it turns out, let's look at some examples. Let's say the derivative with respect to x of x to the 10th power. What is the derivative of x to the 10? 10x to the 9th. Does anyone have any questions on that? By this formula, I take down the power, that becomes my coefficient, x to the power minus 1. So let's look at the derivative, let's say, with respect to w, and let me write w as 1 over w squared. What is going to be the derivative of 1 over w squared?
1 over 2w.
Close.
So w minus 1 or something.
So maybe I should write it like this. The derivative with respect to w of w to the minus 2.
Yeah.
Now what would it be?
2w.
So w is 4 minus
Negative 2w.
Very good. Good. Minus 2w to the minus 3rd. So I could write that as minus 2 over w cubed. But both ways are correct. Do you guys see that? So 2.3.2 specifically talks about integers. 2.2.3 says more so, it doesn't only work with integers, it works with any real exponent. So let's look at maybe the derivative with respect to p of p to the 1/5. What is going to be the derivative of p to the 1/5?
1/5 to the negative 4/5.
Very good. So with fractions, you know, you can write 1/5 minus 1. What's 1/5 minus 1? Well, that's 1/5 minus 5 over 5, which was 1 minus 4. So that's kind of going through that, minus 4 over 5. So you can leave it like that. You could write it as 1 over 5, the 5th root of p to the 4th. So that gives us, you know, something. So let's say the derivative with respect to x of the 8th root of x squared. So I really want to write this as a power. So how could I write it? I could write it as x to the 2 over 8. Right? Or you could write that as this would be 1/4, right? So what's going to be the derivative of x to the 1/4? Right? Can you see that? So don't be intimidated by fractions or anything that looks like, if you think of the b root of x to the 8th power, you can write that as xa over b. All right? So don't be intimidated by things like that. You should be able to rewrite them in a way that you have x to a power. Once you have that x to a power, then the derivative of this, say the derivative with respect to x, of the bth root of x to the a is going to be a over b x to the a over b minus 1. B over b, you know. So then I can write this as a over b x to the a minus b over b. Stephanie, you have a question?
What did you say? Sorry, I just didn't hear you. Did you say you can do the 1 over 5p to the negative 4 over 5p that way? Or would you rather?
Both ways are correct.
Okay.
Generally, we keep it like this
Okay.
because we like to see that p to a power. Writing it like this might help simplify it if it is something. You can plug in your calculator if, like, they ask you to plug in 2, then you take the 5th root of 2 to the 4th, or something like. It might actually end up being something like 2 or something. But this is fine, and this is also equivalent. A lot of times on Wiley, it will say enter your answer with positive exponents. So then you would write it. You could also write it as 1 over 5p to the 4/5, and that would be a way to write it with positive exponents. But if you look in the back of the book or something and they write it like this, I don't want you to think, oh, my answer is wrong. So more than one way to write the correct answer here. So you might not always be given x to a power, but at this point you should be able to simplify it to that form. So let's look at an example. Let's go through one more theorem first. Theorem 2.3.4 is named the constant multiple rule. So if I'm taking the derivative with respect to x of a function that's multiplied by a constant, I can write that as the constant times the derivative of the function. So constants can be pulled out of the function and dealt with later. So let's look at an example. What's the derivative with respect to x of 60 square root of x? So you can just leave the 60. What's the derivative of square root of x? 1/2 x to the minus 1/2, right? Because it's really x to the 1/2 power, so I pull down that 1/2, and then I have 1/2 minus 1, which would be minus 1/2. So I end up with 30 over square root of x. Or I could write that as 30x to the minus 1/2. Both answers are equivalent there. So that constant just means I can deal with it, or I can pull it out, and it turns out simplified in the end.
I'm sorry, where's the 1/2?
Because this is
60 with that.
x to the 1/2 power. So this is the derivative of square root of x, right?
Okay.
So I leave the 60, this constant here. Constant times a function. If you differentiate a constant times a function, it's a constant times the derivative of the function. So if I leave that constant there, and the derivative of x the 1/2 is 1/2 x the minus 1/2, then I can write that as 60 over 2, which is 30, and then x the minus 1/2. Or I can write it as 30 over square root of x. What do you not see?
The 1 over 2,
You don't see this? This is n. N is a half. That's what I pull down. From theorem 2.3.2, this is the formula. X to the n, the derivative of that is n x to the n minus 1. So n here is a half. So n times x, yeah. And then the 60 is just a constant out in front, and I deal with that at the end. So theorem 2.3.5 is the sum and difference rule. Which is what you would expect if I differentiate, let's say f and g are differentiable. At x. And I have the sum or difference. If I'm differentiating the sum or difference of two functions, that's just going to be the derivative of their sum and differences. Right. So what this tells me is I can do it term by term. So if I want to differentiate, say, 5x to the 5th plus 4x squared plus 10x plus x to the minus 3. If I want to differentiate a function that looks like this, I can do it term by term. So what's going to be the derivative of 5x to the 5th?
25x.
Very good. 25x to the 4th. What's the derivative of 4x squared?
8x.
What's the derivative of 10x?
10.
What's the derivative of x to the minus 3? You
Negative 3x. Negative 4.
guys see that? So this theorem tells me I can do it term by term. So what's the derivative with respect to x of pi to the 5th power? What is pi? Pi is a number, right? A number to the 5th power is just a constant, so this is 0. It's the same thing if I would have said the derivative with respect to x of 10 squared. That's not 2 times 10 to the 1st power. That's 0, right? Because 10 squared is a constant. So don't get caught up on doing it so much. I always give this pi to the 5th. It's on Wiley too, and it seems like I probably always have 25% of the class tell me 5 pi to the 4th. But that's just a constant, so you've got to be a little cautious with that. This does not equal 5 pi to the 4th. It's just the number. Why? Pi is a number, 3.1415. It's irrational, it's, but if you plug it in your calculator, it's just a value. If you graph that value, it's a constant. So the slope at any point is 0. Right? If you plug it in, you have pi minus pi over h, which would be 0 over h, as limit as h goes to 0, would be 0. The same thing with, so let's look at the example, the derivative with respect to x of square root of x minus 2x over square root of x. I really want x to a power, because that's the only thing I've learned so far to differentiate using techniques of differentiation. So I need to rewrite this so I have truly x to 1 power. So if I do, if I have a plus b over c, I can write that as a over c plus b over c, right? So if I do that, I'm taking the derivative with respect to x of 1 minus 2x over square root of x. So here, if you remember, if you have x to the a over x to the b, you can write that as x to the a minus b. right? Because I want to get x to a single power. So I could rewrite this as 1 minus 2x to the 1/2, right? 1 minus a half. So now I can differentiate it. What's the derivative of 1? 0. What's the derivative of 2x to the 1/2? Very good. So I'm going to write 2, and then if I bring down the 1/2, x to the minus 1/2. So this would be minus x to the minus 1/2. I write that as minus 1 over the square root of x. But again, multiple ways to write this. So kind of ran out of room there, but so the derivative of 0 is 1. Here I would have 2 times a 1/2, which would then be minus 1, right? Because the negative's there. Anyone have any questions? Yes?
Can you explain what the derivative of that 1 is 0?
The derivative of 1 is 0. Because think of the function 1. That's a constant function. The derivative of any constant is 0. The derivative of 5 is 0. The derivative of pi is 0. This 2? It multiplied by a half because I pulled that half down. Right? So if I write this up here, maybe it would have minus 2 times 1/2 x to the 1/2 minus 1. So yeah, minus 2 times a half is minus 1. And then a half minus 1 is a minus a half. Okay. So in this section, there's a lot of just find the derivatives. But then on top of that, eventually, once we find derivatives, it's like, okay, that's all great, but we want to apply it to something. So generally, we'll apply it to horizontal tangents. Horizontal tangent lines tell us when the slope's 0. So if you think of position and velocity, if you think of a graph, if I differentiate position, I get velocity. So I might want to solve when is the car stopped. The car stopped when the velocity is 0. So if I have a position function, I differentiate it and set that equal to 0 and solve for when that happens. So horizontal tangent lines, you're going to solve for when the derivative of the function equals 0. To think about it, if I just give you a graph, and this is f of x, this point and this point, we'll call it x1, x2, are the points where I have these horizontal tangents. Right? So you solve for when f prime of x equals 0, and your answer is a set of points. X comma f of x. So if we can calculate the first derivative, we can also calculate the second derivative, the third derivative, fourth derivative, fifth derivative, and so forth, right? So higher derivatives on notation, if I have a function, we'll name that function f prime, it might be written as the derivative of f with respect to x. Also might be written as the derivative of x with respect to f of x. This is the first derivative. F double prime, that might be the derivative. Here, this might be the derivative with respect to x of the derivative. And it's written d2f over dx squared. So I'm taking the derivative of this function with respect to x twice. You can think about that as differentiating the first derivative. This is the second derivative. The third derivative is going to look similar. So I'm going to pull this up here a little bit. So f triple prime is going to be It's going to be the derivative with respect to x of the second derivative. After the third derivative, we stop using these tick marks and we use something that looks like this. The fourth derivative. And we can say the nth derivative. This would be the general nth order derivative. Right? So you just keep differentiating. So we have first derivative, second derivative, third derivative. After that, we use this f of a power to the parentheses, and that means the fourth derivative or the nth derivative. We might also say, you know, find the derivative and plug in the point x equals x naught. This is the derivative at a specific point. X equals x naught. This is going to give you the slope of tangent line at x naught. Does that make sense? This is just some notation. And you'll see this on Wiley. You'll see it in your book. So you want to use it if I say, okay, I want to evaluate this function at this point. I'm going to have the derivative, and then I make a vertical line and say x equals 5. So I'm plugging 5 into that function. So let's look at example number 8. So it's the application in example number 8 is find the area of the triangle formed from the coordinate axes and the tangent line to the curve y equals 5 over x minus 1/5 x at the point 5, 0. So what I'm doing here is I have this function y equals 5 over x minus 1/5 x. And I'm looking at this point 5, 0. There's a tangent line at that point. So if I draw the tangent line here, I'm looking for the area of the triangle that is enclosed by the coordinate axes, so the y-axis and the x-axis, and the tangent line to this curve at this point. So how do I find the area of a triangle? Very good. So I have area equals 1/2 base times height. What is the base of this triangle? 5, right? What is the height of this triangle? We don't know because I don't know where this intersects, because I don't know the equation of the tangent line. But if I find the equation of the tangent line, I can find the height. So you can see here how it's not exactly saying find the derivative. But you have to find the derivative to find the slope. You have to find the derivative at the point x equals 5 to plug that in to find the slope. Once you have the slope, you have a point and a slope, you can find the equation of the tangent line. If you write it in y equals mx plus b format, you'll get the y-intercept, which is exactly what you want there. So what is the derivative? So y is 5x to the minus 1 minus 1/5 x. What is the derivative of y?
-5x to -2 minus 1/5.
Very good. And I'm going to evaluate that at x equals 5 because that's going to give me the slope, right? So if I plug in 5, I have 25. Sorry, I have 25. I have negative 5 over 25. Right, because I could write this minus 5 over 25 minus 1/5. So really it's minus a fifth minus a fifth. So it's minus 2/5. This gives me my slope. And I have a point. Does anyone have a question where I get this minus 2/5? I just plugged it in 5, right? So I have minus 5 over 25. Because 5 to the minus 2 is 1 over 25. 5 squared is 25, but it's in the denominator. Minus a fifth. So this would simplify to minus 1 over 5 minus 1 over 5, which is minus 2/5. You can plug it in your calculator. Your calculator should be able to evaluate it too. If you have minus 5 times 5 to the minus 2 minus a fifth, it should tell you minus 2/5.
Why are we plugging in 5?
We're plugging in this 5 is because we want to know the slope at x equals 5. Because we only care about the derivative at x equals 5. Because that's going to be the slope of the tangent line at that point. So I have a slope and I have a point. Question?
What happened to the x when you went from the other one?
This x? I differentiated it. What's the derivative of x? 1. Right?
Oh,
Because it would be really x to the 1 minus 1, which would be x to the 0. X to the 0 is 1.
okay.
This is a good question, though. I'm differentiating this whole function. This term, minus 5x to the minus 2. This term would be minus a fifth x to the 0, and x to the 0 is 1. So if I plug in 5, I get minus 2/5. Is everyone okay now on that point? If something doesn't make sense, let me know. So now I need the equation of this tangent line. The equation of the tangent line would be y minus y1 equals my slope x minus x1. So I'd have y minus 0 equals minus 2/5 times x minus 5. So I get y equals minus 2/5 x plus 2. That's my y-intercept, right? So that tells me my height here is 2. So to answer the question, it's looking for the area of the triangle. The area of the triangle is 1/2 base times height. So the area here is 1/2 2 times 5, which would be 5 units squared. So your answer is 5 units squared. The area of this triangle is 5 units squared. But it takes quite a bit to get there. You need to know that I need to evaluate the derivative. I need to evaluate the derivative at x equals 5 to get the slope. Once you've done that, you're pretty much close to point slope form, and then get the y-intercept. The y-intercept is when x equals 0. So if I plug x equals 0, y equals 2. Question?
So that's that other point that's on the...
The 2 is the y-intercept of the tangent line.
How did you get this?
This slope, minus 2/5. I plugged in 5 to this function. So I have minus 5 to the 5 to the minus 2. 5 to the minus 2 is 1 over 25. So minus 5 times 1 over 25 is minus a fifth. So then I have minus a fifth, which is minus 2/5. Question?
If it was a negative, are we taking the absolute value of the constant with the y-intercept?
If
The triangle were
no.
a different point.
If it was negative, well, you can't have negative area.
Yeah.
So you could have a triangle that was down here, and if it asked for area, you would just take the length, your height, your height times your base. But it's gonna, if you have that negative, you take it as positive distance. That's a good question, but your area is always positive. You wouldn't think of it as absolute value. You think of it as what's the distance from here to here. The distance from here to here is 2, and we get that because the y-intercept's 2. But if it was down here, the distance would still possibly be 2, just because it would be at negative 2, which would be fine. The distance is 2. Okay, so I want to pull up some Wiley questions. I always get logged out. So Wiley, section. So you have 2.3. 2.3 is pretty straightforward. Find the derivative. So what would be the derivative of this function?
16x plus 2.
Good. 16x cubed plus 2. Right? Here, the same thing, very similar. This 1/2, you can multiply it through and just have a polynomial, or you can use that constant rule, constant times the derivative of the inside, and simplify it. What's the derivative of pi squared? 0. So don't put 2 pi to the first. One I want to go over that is a little bit interesting how you input it is this one right here. So let's look at this problem. What is going to be the derivative of x to the e? Very good. Ex to the e minus 1. So you're going to enter it as ex to the e minus 1. And that's perfectly fine. Okay, what's going to be the derivative of 1 over x to the square root of 10? Very good. Negative square root of 10. X to the minus square root of 10 minus 1. So this doesn't look, the prettiest, but it is correct, right? I take down my n, x to the n minus 1. N here is just e. In this example, n is minus square root of 10. So I bring down the minus square root of 10, x to the minus square root of 10 minus 1. Right?
I know this is just a simple algebra question, but since it's 1 over, that means it's negative.
Yes. So very important. If I have 1 over x to the a, I can write that as x to the a, x to the minus a.
And then the 1 is like over the square root of x.
That would be x to the minus 1/2. Okay, so if I submit this, you can see that it's going to accept it as the right answer. So this is the only one that's a little bit interesting the way you input it.
Will it take it if you use those square roots as like powers instead?
If you put like 10 to the minus 1/2 or 10 to the 1/2,
Yeah, like 1/2.
possibly. I think it probably should. If you're careful with your exponents in your parentheses, if you say do that. Yeah, it should take it. If not, let me know. So most of them are pretty straightforward. The next example here, when you have a product, it's going to lead us to our next section on 2.4, the product rule. Because eventually the derivative of the multiplication of two functions isn't the multiplication of their derivative. It's more complicated than that, and we're going to go over that tomorrow. So you can look at this example, and we'll cover the product rule and the quotient rule the rest of this week, and then take exam 1 on Thursday. And I didn't pass around the sign-in sheet, but that's fine.